Is it going now?
It's going now.
Oh my goodness.
So the red light means you're recording.
That means I have to start watching my mouth.
Well,
okay.
I can delete whatever.
All right. Oh yeah, we'll fix it in post. Fix it in post. And then when I'm done, I hit that stop button?
That's it. And then the red light will turn green, and the light is green, the trap is clean.
Light is green, trap is clean. Can you see this I'm going to sit this over here to the side. All right. Oh, I can already tell that marker is not going to work.
I think I found it.
All right. Testing. All right. Is this on? I'm going to do this. Oh, yeah. Oh, yeah, that's totally on. Okay. Yeah. I got to get my... Okay. Yeah. Welcome, everyone. Yep. Nope, don't mess up. All right, I'm going to give you just the super, super quick version of circuits, and hopefully it'll just cover whatever it is that you need to know to get ready to win State College Bowl. So here we go. I'm going to give you first, before I start with the slides, I'll give you like the best, tiniest little introduction that I can possibly give you about electricity. The biggest thing you need to remember, like when you're starting out learning about circuits, all electricity is moving electrons. That's all it is. All right. Anytime somebody says electricity or anything like that, it's just a bunch of electrons moving through a wire. Okay. And we'll go into there's basically, I think, 4 variables probably that you'll need to be aware of. Then we'll go over the 2 types of circuits, and then we'll do like a little sample problem or something like that with each one. It should be good. All right. So think about this. You have electricity goes through a wire. All that's happening is those electrons are carrying electrical energy. That electrical energy is going to hit an appliance, and then that electrical energy just gets converted into some type of mechanical energy that then explodes into life and begins. You can do whatever it is that you want to do. Run a vacuum cleaner, make a delicious salsa in a blender. I don't know, whatever it is you want to do. Turn on your microwave, fine. Okay, so that's all that is. Now, I'll go over, this is going to kind of start halfway through, but I want to go over 2 other, well, I guess really for now, just 1 other variable before we start and get into this. That variable is this. It is voltage. Oh, this board is all bulged out. Did you notice that? All right, voltage. All voltage is. It is basically like electrical potential energy. Okay. In order for you to have an electrical current, you have to have electrons. They have to be able to move, but then they have to have a reason to move. Okay. They don't just move on their own. You gotta give them a reason. Okay. And so that reason is going to be voltage. Okay. Think of it like potential energy. So my analogy that I always use to this is if you go up to the top of the school and you stand on the roof and you're just about to fall over, okay, you're not going to fall over unless you get that push, okay? Someone pushes you up the ledge, then you'll begin falling. Think about the fall as the flow of current, okay, electrical current through a wire, through a circuit, and then the push is going to be that voltage. Okay, you have to have a reason that you started falling in the first place. All right? And so voltage in terms of electricity just means all they're going to do is on one side of whatever circuit you're talking about, okay, there's going to be negative charges, and on the other side there's going to be positive charges. Well, electrons, because they all follow Coulomb's law, everything does. It's not Coulomb's great suggestion, it's Coulomb's law, baby. All right, so that means opposite charges are going to attract, like charges are going to repel. So electrons are going to always go from the negative side and then flow to the positive side because they'll be attracted to the positive charges and then repelled from the negative charges. All right, so that's what makes a current go. All right, so how much or how big those sides are, okay, how charged up each side is that makes the current flow through a circuit, that's referred to as voltage. Okay, the higher the voltage is, then when you give those electrons a pathway, the faster they're going to roll through that circuit. Okay, so that's pretty much all voltage is, and we'll put it into equations here in just a minute. Second one is going to be resistance. That's this guy. Okay, And I should say, first of all, probably what you'll want to know, now don't mix up, and I tell my science kids this all the time, don't mix up the symbol with the label. Okay, the symbol for voltage is V. Okay, so you see V, it means voltage. The label is going to be volts. Okay, and that's pretty much all you need to know about that. Resistance. Resistance is the next one. Okay, its symbol is going to be capital R. All right, and its label is going to be ohms, which in, I don't know, layman's terms, or my terms, not really layman's, worse than that, is going to be upside down horseshoe. Okay, that's your label for ohms. I think it's called omega, but I don't know, and I don't care. It's fine. It's this. Okay, this is your label for resistance, and then your symbol for that is going to be R. I'm just going to leave that there. Okay, don't worry, I'm building towards something here. All resistance is going to be resistance to electrical current. Okay, in other words, resistance to electrons flowing through that wire. Okay, because electrons literally moving through, or I guess you say along the surface of a material is going to create friction. Okay, that's going to provide some natural resistance. Okay, so every material is going to have some sort of resistance to that flow. But that is important if you're trying to figure out a lot of the math that's involved with current and voltage, and then resistance for a given electrical circuit, which is something that you're going to need to be able to calculate. So that's all this slide says. You can always pause it right here and read through these notes, but all it says, symbols are unit ohms, which is, and the label is going to be upside down horseshoe. Okay, and then resistance itself is just opposition to electrical current. Now, this shows you, this is what's called Ohm's law. This is probably the main equation that you're going to want to be able to roll through if they give you these circuit questions. Okay, and they show it to you in terms of R initially. A lot of books do this. A lot of, accompanying notes do this. I don't like this form of the equation just because fractions are bad. So this is what I do. I know it as this. Okay, all I'm going to do is solve this thing for change in voltage. As you guys know, triangle anything means change in, but you'll end up just shortening it so that it's just V. Okay, and V is going to be equal to IR. Okay, that's huge. That's what you want to know. And I just know it. V equals IR, V equals IR, V equals IR. Okay, and that's basically my version of Ohm's law, just because it looks a little bit tighter. I like it like that. Yeah. So, all right. Some of these slides we're going to skip. You don't really need to know about this. You don't really need to know about resistance. Too much more about resistance other than what we just went over. Let's see. We talked about current. I do need to go back and talk about current. That's the third one. That's the third symbol that you guys are going to want to know about for these. For the V equals IR. You know about V, you know about R, and now we need to cover current. Current, okay, it would be really easy if the symbol for current was capital C, but we're not going to do that. All right, instead, the symbol for current is going to be capital I. Okay, so just keep that in mind. That means current. And all current is the rate at which those actual electrical charges, meaning those electrons, all right, go through a specific area of a circuit. Okay, so symbols I. The label for this is going to be amperes, which you call it A. Okay, you probably heard the term amps. All right, that's what cool people use because they don't have time to use the whole word. So I'll call it amps. I'll just say amps. There you go. Yeah. All right. So that's the label. The symbol is I. And so you won't need to know this equation. This just kind of gives you a basis for how current is calculated. Just charge passing through an area over a given amount of time. So really what we're chasing is we want to look through these three symbols and then incorporate that into, again, V equals I, R. Okay, that's what we're looking at. So you have the basis of how all these things, how you're going to use this equation. And now I'm going to take these guys and show you how you calculate them for each of the two circuits that you can have. Okay, I'm going to roll through a lot of this. If I don't cover it here, then if these slides get printed out in your notes, don't worry about going over those, okay? We'll go over them later, but it's not stuff that you need to know just for this situation here. Types of current. We're just going to go over this real quick. There are actually 2 types of currents that you can have going through a circuit. You are not going to be asked to do anything about alternating current, so don't worry about it, okay? It is actually awesome, but forget it. We're going with direct current because it's easier to do the math related to direct current. So that's all we're going to be dealing with. Now, there is, Wahlberg said that you might see something about electrical power, and in case you do, they ask you to calculate power. All this is any type of power that you see, and the people who have been in physics, the Macy Steinloggies of the world, know that any type of power is just the rate, okay, so per time, the rate at which work is done. Well, it's not really any different here, okay? Electrical power is just a more specific type of power, but it's the rate at which electricity does work, okay? So it's going to be that electrical energy that we talked about before being transformed by some device per unit time. And I mean transformed into some other type of energy. It's usually some form of mechanical energy, okay, per amount of time. Symbol for electrical power is P. Okay, and then the unit, just like any power unit, is going to be watts. It's always watts. So I know a lot of times they'll ask you, if they ask you to calculate this, and you come up with an answer and you're just like 5. They won't count it right because you didn't put the unit with it. If you need to, say, oh, it's watts. Okay, that's the unit for power. The equation for power, the one that I would remember, and probably the only one that they would be anywhere near asking you to calculate would be this guy, because this relates to your V and your I for this situation. So electrical power, all you have to do is multiply the current and the voltage. It's just I times V, okay? So no problem. They give you a current, they give you a voltage, it's P equals IV. And you'll see this. I'm going to hand out to you like a little worksheet where you guys can kind of roll through some of this, but I also have an equation sheet that I'll give to each one of you so that you can look through that equation sheet and just kind of see what types of equations you want to be aware of. It's not really that much. You probably have V equals IR you'll want to know because that's a big one. And then P equals IV, all right. And then you just want to know how to calculate resistances, which I'm going to talk to you about here in just a second. Okay? I wouldn't worry about any of the rest of this. You can go through these. You can go through these questions if you want, but again, you're going to have stuff on your worksheet, so you're not going to need to worry about that. Okay, electrical circuits. Electrical circuits, all right, all have kind of the same. They all conform to the same set of rules in terms of how you draw circuits and the symbols you show and what those symbols mean. And even though they're probably not going to give you they're not probably going to show you a picture and ask you to calculate. They'll just give you like an oral form of a question, and you just have to roll through it. But it is kind of helpful to be able to envision these simple circuits in your mind. So all that's going to happen in this, the only components that you're going to need to worry about is straight line. That just means that is showing you a pathway that electrical current is going through. That's all that shows you. Anytime you hit a device or a resistor, anything, okay? Anything that has like specific resistance with it, you're going to show with a squiggly line, okay? Sometimes in a circuit you can actually just put a resistor and its only job is to just offer resistance, okay? And there'll be reasons for that you don't really need to worry about right now, but sometimes they're there. It's important to remember that any device you hook up to an electrical circuit, okay, whether it's a vacuum cleaner or a microwave or a hair dryer or a curling iron or something, each one of those devices will have resistance as well. And you can show those with this same squiggly line. Okay? Means everything. Let's see. The only other one you'll need to worry about here would be this little symbol right here. This is a power source. Okay, and that just means you're going to have maybe it's a battery, maybe it's a plug-in, maybe it's the actual electric company, whatever. Just means every circuit has to have this, or else, like I said, this power source creates your voltage. Okay, and you have to have voltage, or else there's no reason for electrons to go through this wire at all. So every circuit has to have one of these. And it's important because they're all going to be associated with some type of voltage, and then as you know now, you need that to plug into these equations. Okay? The only other thing you might need to know for some of the problems we're going to go through is the difference between an open and a closed circuit. Closed circuit means that wire is totally complete, and so that means all the current can flow through it. You can read through maybe just this note, but if I make a circuit here, all right, very simple. I'll put a little resistor in there. Okay, little squiggly line. So this thing is closed. This is a closed pathway. This means current's going to go all the way around here. You have your power source, which you have to have. All right, 'cause it has to have that reason. That'll be associated with the voltage that goes along with the circuit. As long as this thing is closed, current's going to go through it, no problem. If you open the circuit, that would be, you'd show that schematically by doing this. That means now the electrons cannot get through here because there's a little gap. Okay, it'd be like a giant log laying in the middle of a road. Okay, you can't get through. So these electrons have to have a pathway in order to get all the way around here, around this circuit. So if they don't, that's an open circuit. Nothing's going to happen. Okay, you have no current there. So just to kind of give you a little bit of a background on some of that. So any electrical circuit's going to contain one or more complete pathways for electricity to go through. So don't need to worry about this. Okay, here's the last thing we'll go over. These two types of circuits, series and parallel. Here's what a series is. Okay, series circuit only shows one path, okay, from the battery, just one pathway, and that's it. You can see in this example here, you have your power source, which you have to have, and then, but look, there's only one total pathway there, one little line. Okay, so this is the only option for electrical current, for electrons, to go from one side to the other, okay? And actually, I probably should have it show my finger going this way, all right? But anyway, there's only one pathway. The directionality doesn't really matter for you guys because the math is all going to work out the same, and so I'm not going to go into any other detail past that. But series circuit, one pathway. And then you're going to see one of the differences between a series and then a parallel, which we're going to talk about next, is that a parallel circuit has multiple possible pathways, okay, for current to go through. Series just has one. All right, so because there's only now, for each, I'm going to say this, for each circuit we go through, for each type, this is series, I'm going to go through voltage, resistance, and current, and talk about how to just calculate those things. Okay, so real quick, if you have just one pathway, okay, that means there's only one way for all that current to go around in that circuit. So that means, okay, at every single point on this pathway, you will have the same amount of current flowing through it. Okay? The current can't break off because the current is associated with the actual physical electrons going through here. Well, there's only one pathway for them to go. Okay? You're not going to have electrons stop in the middle of the circuit, you know, and pull off at the electrical circuit equivalent of a gas station and get a soda. That's not possible. Okay? So, these guys are all going around here so that every point you have one current. Okay, the current here is the same as the current here, is the same as the current here, 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 and here. Okay, so keep that in mind. All of these three little squiggly lines, these are three different resistors that are hooked up into this circuit. And what they'll want you to know is kind of a basic type of calculation you'll have to do with electricity is looking for each one of these resistors. You will want to figure out, okay, or they may ask you to figure out either the resistance associated with it, okay, which would be a number, okay, in ohms. They'll ask you how much current is flowing through that, okay, and for this one it's going to be an easy one, I'll show you, but that's in amps. And then the last thing is they may ask you the voltage drop across each resistor. Okay, so think about that phrase, and I'll go through and I'll explain that here in just a second. Right, so each one of these things you're going to have a value for voltage, a value for resistance, and a value for current for each one. Okay, and based on this equation right here, if you know two of them, then you can figure out the third one. And so these circuits just kind of turn out to be just like little mini puzzles that you're just trying to solve and figure out. You find 2 of these for any one of these resistors, you can find the third one. Okay, and so all these tips will help you figure that out. So the current across each one of these in a series circuit is going to be the same. Why? Because there's only one pathway. So the current has to be the same. So the current associated with this guy is the same as the current associated with this guy is the same as the current associated with this, because they all have the same amounts of current going through them. All right? So there's that. Let's see. In terms of voltage, okay, this is what we say here. Your note, they all are going to share the entire voltage that is provided by this battery, okay, that entire electrical potential. All right, so if they tell you that the voltage here for this battery that you hook up in here, let's say, is 9 volts. Okay, if it's 9 volts, then that means this. The electrons coming out of here, all right, are going to go through each one of these resistances. Each time they hit a resistor, they are going to undergo a voltage drop. All right, and what's going to happen is when you add up these 3 voltage drops, so the voltage is going to drop a little bit, and then a little bit more, and then a little bit more. But once they get past all of the resistors and they have nothing left to go through except just wire and then back to battery, their voltage should be at 0. Okay, so follow me around this circuit. These guys, these electrons come out of here. Okay, they have 9 volts of potential energy. 9 volts, 9 volts, 9 volts, 9 volts, 9 volts. Nothing weird going on here. 9 volts, 9 volts. Now they hit a resistor. They are going to drop by some amount. Okay, we don't know yet. We'd have to do some calculations to figure that out. But if it did, okay, and I'm just going to make up a number now just to give you an example. Let's say the voltage drop across this is 3 volts. This thing drops by 3 volts, and that means the current here, okay, before it hits the resistor, 9 volts. Goes through this resistor, and now, right here, the current in this little segment of the wire is now down to 6 volts. Okay? Then it hits this thing. Let's just say that the voltage going through here, let's say, is across this resistor is going to be 1 volt. Okay, fine. Goes through this resistor. Now the current after that now is down to 5. That means that this resistor will have to be responsible for the remaining 5 volts, okay, of potential drop, so that when it comes out of here every time, and this is you might as well just call it a law. I don't know if it is, but whatever. Every time these currents come out of here and they have nothing left between wherever the wire is and then the battery, all of this current is going to be at 0 volts, okay? And it's going to go into the battery, then it will go back up. So I always make an analogy. Think about it like a building, okay? In the Bugs Bunny cartoons where, Yosemite Sam goes up to the highest point of the building, he falls off. He falls all the way down. Then he goes into the building, gets in an elevator, goes back up, goes to the top, falls back down again. Then he gets in an elevator, goes back up. It's the same situation, okay? So you're at the top of the building here. Top of the building, top of the building, top of the building. Okay, you can't say, regardless of what pathway you take down, right, you're going to end up at the ground floor if you're all the way at the bottom. You got to end up there. So think of these resistors as just different amounts of floors that you're falling. If this is a 9-story building, you fell 3 stories, then another story, and then the remaining 5 stories. And I'll even draw this out here just for completeness sake. So once you get here, you're at the ground, okay? You go back inside the building, you get in the elevator. This elevator takes you back up to the 9th floor, or the top floor, which would be floor 9 in this example, okay? So then you just go through the whole thing again, right? But altogether, when you add up your voltages for each one of these resistors, it has to equal this total here, okay? So that's just another little tip, little trick to help you put some of these values in here so that you can use V equals IR. The last thing we'll go over for series circuit is going to be calculating what they call equivalent resistance. All these circuits may ask you to find the total resistance associated with that given circuit, okay? And in order to calculate equivalent resistance. And so you can think of equivalent resistance, another way of saying it is just total resistance for a circuit. Okay? Each one of these resistors has their own amount of resistance to it. But then there is also a total amount of resistance associated with the circuit altogether. So you calculate, and the first thing you do when you're trying to figure this out is you think to yourself literally, is this a series circuit or is it parallel? The questions you will be asked will tell you. It will usually say you have 3 resistors connected in series right there. You say, oh, series circuit. Okay, if it's a series circuit, then you know you can use this little handy equation here. Okay, don't hurt yourself. All you're going to do to figure out equivalent resistance is add up the resistance in each one. If it's a series circuit, you just add the resistances together, whatever they are. Add them up, and you're gold. You got it. Okay, so that's pretty much it for series circuits. Okay. All right, so one real quick, just a little example, very simple. You have a 9-volt battery, okay? Interesting how that worked out. 9-volt battery, and then it's connected in series with 4 light bulbs as shown. If you have to find the equivalent resistance for this entire circuit, all you're going to do, add the resistances together. 2, that's a 2, trust me, plus 4, plus 5, plus 7, and you got it. I'll give you a second to do that math. Good, all right. So now you found equivalent resistance. If you know the equivalent resistance, okay, check this out. Okay, you know 9 volts, okay, is going to be the total voltage in this circuit. Your equivalent resistance, you're going to go 4 plus, I should add them in order, it'll help you. 2 plus 4 plus 5 plus 7. Great. Add that together. 12, 13, 14, 15, 16, 18. I did it. Okay. Now look at what you have. You have, I don't need to do that. You have R here, that's this. You have V, jam it in there, find the current. The current is going to be I. Okay? So, stick that in there, put your 9 in there, find your current. Okay? Nice and easy. All right. Last thing, I don't know if they'll ask you any information-y questions that are associated with circuits, but just keep this in mind. There's only one pathway for current. If that pathway gets messed up, no current will flow. It just cuts everything off. Okay, so if you have a circuit like this, series, it's all series, there's only one pathway. If this light bulb goes out, okay, this is the much maligned Christmas tree light problem. All right, this thing goes out, nothing works. And then the problem is you don't know which one it is, and then you got to waste most of your holiday trying to figure out which of these lights went out and replace them or anything, but that's not really related to anything you care about right now. So, I have a couple of these little examples you can go through, and if you have any questions, you can ask Wally, who knows some stuff, or you can text me and I'll help you out. Here's the second example. Okay, this is the last one we'll go over. Parallel circuit. The only difference. Series circuit, one pathway. Okay, one pathway for current. Parallel circuit, multiple pathways. Okay, it's got some choices to make there. So all that's going to happen if I follow this current around through this circuit is going to go like this. Okay, here comes your current, here comes your current, here comes your current. Now up to this point, one pathway. Okay, so nothing weird going on here. Okay, all very just normal, regular, and then it hits this little junction. Okay, now it's kind of like a fork in the road. It's got 3 choices. All right, so what pathway this current is going to take is going to depend on a number of things, but the point here is that this current, whatever this total amount of current is in this wire, it will split. Okay? Not necessarily equally. You'll have to do math to figure out how it's going to split, but it's going to split up so that part of the current goes here, part of the current goes here, part of the current goes here. Okay? That's totally fine for it to do, but it will always do so in a way that if you add these currents together, it will equal the total current going through here, okay? You got to keep all that stuff, this all conservation of things like energy and mass and all that stuff, okay? So it will split, but if you figure out the current going through each of these little segments, each of these pathways, it will equal the total current, okay? Now, each one of these parallel pathways, you have one resistor. Look at that, okay? That's where it's going. It will go through that, resistor, and then it will come back together. All this current will come back together. And so let's say, okay, and this is all additive, if your current here is, let's say 9 amps, if you have 9 amps of current going through here, then that means when all, okay, it'll split up. And I'm just going to make up some numbers. Let's say it's, well, you got 1 amp here, you got 6 amps here, and then you're going to have 2 amps here. Fine. Okay? It's not, I didn't do any math, it just totally pulled out some numbers. But I did those numbers, or I put those numbers on here so that when they added them up, it would be 9. They go through their respective resistors, they come back together, and now you're going to be right back to 9 amps, and then 9 amps goes through there. Okay? So, keep that in mind for current. Now, here's where it gets a little weird. Okay? Let's do resistance first, the resistance of each of these resistors, okay? No big deal. You'll have to go through and you're going to have to find some other numbers and then use this. You can use this equation for each individual resistor, okay, to figure out all of these 3 unknowns associated with each resistor, but you can also do this for the entire circuit as I showed you in the last example. So each one of these resistors will have a resistance associated with it, no big deal. Here's where it gets a little weird. Voltage, okay? Don't get freaked out. Okay, keep it together. If your voltage, let's say, is 9 volts, okay? 9-volt battery, the old 9-volt battery. All right? You have voltage, 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 voltage. As long as it doesn't hit a resistor, that current is going to be at 9 volts. Okay, so 9, 9, 9, 9, 9. 9 volts, 9 volts, 9 volts, 9 volts, 9 volts, 9 volts. Remember, if you hook any resistor up to this thing at all, that resistor is going to be responsible for a voltage drop. And the other rule is, when your current gets back here, right before it goes in the battery, so everything from here onwards, look, this current has nothing else to go through. It's just wire. Okay? When it gets over here, the voltage over here has to be, this is just the way God wanted it, has to be at 0 volts. Okay? So whatever it goes through, when it's here, 9 volts, 9 volts, 9 volts, all right? Whatever resistors it hits between the beginning and the end has to be responsible for all 9 volts of drop. So, if you only have one resistor in each one of these pathways, that resistor then has to be responsible for all 9 volts of drop. If you only have one, all these resistors will be responsible for the same voltage drop, which in this case is going to be 9. Okay, because it has to be 0 when it gets past all these resistors to the point where the only place left to go now is back into the battery. Okay, so that's what these guys mean. Resistors in parallel have the same potential difference, same V drop, okay, across them. And then the sum of the currents in each parallel pathway is going to add up to your total current. So that's no big deal. Last thing here is going to be total resistance. If you need to find the total resistance, in other words, the equivalent resistance, that's what this is. Being total. All right? Kind of a weird equation for it, but this is what you do. You want the total equivalent, the total resistance in this wire. You're going to take this guy, this guy, this guy. You've got to find these first, and you're just going to plug them in here. Okay? 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance. And then you would keep going if there were more pathways and resistors and blah, 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 blah. All right? Just keep in mind, if they give you this and you add this up, when you just add these, okay, it's not straight up going to give you R. It's a mistake that people are going to make. And I would guess that one of the things Scholars Bowl would try to get you with is they would have you, okay, 3 pathways, 1 resistor each pathway, you'd add all these up, and they want to see if you just add these up and you're all excited, you hit the button and you give them whatever that sum was. That is not correct, okay? It's not equal to that. It's equal to 1 over that. So you've got to make sure that after you add these up, take the reciprocal, okay? Do 1 over that. That's going to give you your equivalent resistance, okay? So just watch out for that. Okay. You probably don't need this other than if you want to look at some awesome animation that you can just stare at for a while. That's fun. That should pretty much cover it. Let's see. If you want to go through here, check this little example out. I'll give you one real simple one. Okay. 9-volt battery. Okay. Hooked up in parallel as you see here in this wonderful rendering. find the equivalent resistance for the circuit and then the total current. All right, so I didn't have enough room, but I'm going to show these. These are all the resistances for each resistor, okay, and then, okay, for each one of these, and you have, 4 pathways, okay, no problem. So, if you want to know the equivalent resistance, very easy. Look at all these guys. You're just going to go 1 over 7 plus 1 over 5 plus 1 over 4. I think that's a 4. It looks like a 4. Let's look at it again. Yeah, that's probably a 4. 4 plus 1 over 2. And remember, that's going to equal 1 over your equivalent resistance. Okay? So once you add these up, you get this. Take the reciprocal, and then you're golden. All right? Now, you would have the total equivalent resistance, total resistance for this circuit. You know there's going to be 9 volts of potential drop in here. So now check it out. You just found that. You just found that. And now you can just figure out, go through, plug those in, solve for I. That gives you your total current running through that circuit. If they ask you something, tricky, like what's the potential drop across each resistor? It's 9. It's easy. There's only one resistor, okay, regardless of what pathway this current chooses. It can't turn around and go backwards, okay? These are all one-way streets, all right? So, voltage drop across each one is going to be 9 volts, okay? 9 volts, 9 volts, 9 volts, 9 volts, a little repetitive. And now, if you wanted to, okay, you wanted to get weird with it, now look, you could figure out how much of that total current is going through each one of these resistors. Why? Because, look, for each resistor here, you have an R and you have a V. Then you can just plug it in, find I. You do the same thing with this one. You got a V, you got an R, find I. You got a V, you got an R, find I. You got a V, you got an R, find I. If you add up all these currents, okay, it should equal, it had better, your total current going through that wire that you calculated initially. All right? The nice advantage to having a parallel circuit, okay, this is the reason why this happens a lot, all right, is because, look, you got all these pathways. If one light goes out, doesn't make any difference. It's going to go through all the other bulbs, okay? Yeah, that pathway is not going to work, but the other ones will, okay, because they're parallel pathways. It's just got, choices. Okay, so all I did, and you guys will see this in the little note packet that I'll give you, this is just a nice, now unblemished with marker version of what I'm talking about here. All right, where you have all of this. This is a nice little review slide. I'm a big fan of those, okay? And so you can go through and figure that out. Now would maybe be a good time. You can pull out the little worksheets that I'll give you. You can ask Wally for the answers once you try to figure all this stuff out. You have an equation sheet that I'll show you. You'll have the note guide so you can even follow along. So many resources. And if you have any questions, you can text or email me or whatever. All right? That's it. I don't know how to hit stop on this thing. We'll fix it.